I don't know.
Good morning, everyone. Okay, today we are going to start section 3.9. Okay, we're going to talk about the derivative of the logarithm and the exponential function. And exponential function in general. All right, so first we start with the exponential function. What do we mean by the exponential function? It means what we've seen so far, if f of x equal e to the x, the base is e, then the derivative is e to the x. We've seen that. Okay, today what we're going to see is the following. Suppose we have an exponential function f of x. It's not e to the x, it's another base, like a to the x, like 2 to the x, 4 to the x, 5 to the x. Then the question is, what is the derivative? Okay. All right, so we're going to proceed as follows. I'm going to write something on the sheet of paper and you tell me if it's right or not. First, a to the x. So that's my question. What's the derivative? I'm going to rewrite it like this. E to the power ln of a to the power x. Is this true or false? Okay, is this true or false? So is a equal e to the ln of a? Anybody? I know it's Monday. Anybody? Okay, let us remember. If I take e to the ln of 2, this is 2. E.
So that well, I guess it doesn't really matter. You can just help me. But
Yeah. I don't even know if I have a fuck.
Okay. E to the ln of 3 is equal to 3, and so on and so forth. So e to the ln of a is equal to a. What's the benefit of that? The benefit is the following. I'm going to rewrite this as I'm going to use the property of the power. E to the ln of a, we multiply the power. Remember, ln of a here is a number. So now let's find the derivative. What is f prime? It means what is the derivative of a to the x? Sorry. So that's equal to the derivative of e to the x ln of a. And now the question was the derivative of this function. All right, we're going to use the chain rule. So what's the chain rule? Chain rule. I have an inside function. This piece right here is going to be my inside. That's the inside function. So it's going to be the chain rule. We use it like this. The outside is e to the u. The inside is the x ln of a. So what's going to be my derivative? So it's going to be the derivative of the outside, which is e, evaluated at the inside, times the derivative of the inside. So this is the inside is x times ln of a, but ln of a is a constant, nothing more, nothing less. So this times ln of a. And now the last step in here, this is going to be equal to e to the x ln of a is nothing more than a to the x times ln of a. So we have our first formula for this, that the derivative with respect to x of a to the x is actually ln of a, which is a constant, times a to the x. So watch that in particular, if a is e, it's ln of e times e to the x, but ln of e is actually 1, so we don't really have an issue with that. Okay, so it coincides with what we know. All right, let us practice this formula a little bit. Let me take.
I have a question.
Yes, please go ahead.
I can't read it, but what's the outside and the inside?
Right
the
here.
chain rule.
Right. Let us think a little bit. Right here, right?
Yes.
Okay. So let me ask you a question before I do that. Suppose I have e to the 2x. All right? And then I'll come back to this. Okay, I want to ask you to find the derivative of that. What's the derivative of e to the 2x?
Wouldn't you have to use the chain rule?
Yeah, what's your inside?
2x.
Right, what's the outside?
Just e?
E to the,
or
no, doesn't make sense. E to the u.
E to the u?
Yeah.
Oh, okay, okay.
This is your u. Then the outside, e to the u, the exponential, and the inside is 2x. Correct?
Yes.
Okay, but if I have e to the 3x, will it be the same picture? If instead of 2, I have e to the 3x, will I repeat the same thing?
Yes.
Very good. Now here, a is a constant. It's like 2 to the x, 3 to the x. ln of a is also a constant. So it's like, depends on a. Like if a is 2, it's ln of 2. If a is 3, it's ln of 3. It's actually nothing more than a number. It's just like a 2 in here, just a constant. So what does this mean? That the inside is going to be the same thing you told me the inside here is 2x. The inside here is going to be x ln of a. The power, the exponent, this one. And the outside is e to the u. So when I'm finding its derivative, it's going to be the derivative of the outside, which is the exponential evaluated at the inside, times the derivative of the inside. But the derivative in the inside is x times ln of a. So the derivative is going to be the constant ln of a. Okay, does this answer your question?
Yes, thank you.
Sure. So now let us take 2 examples to elaborate this. It's just a formula, basically, that we're adding to our collection of formulas for the derivative. And we still have basically 2 more formulas almost. And we're done with this stuff. So let's do example. I'm going to keep this in front of me and practice it. It's ln of a. Remember, ln of a is it times a to the x. All right. So let's practice this. So example, find the derivative of each of the following functions. So find the derivative. So I will take the following, f of x equal verbatim application, 10 to the x. Remember here, the power itself is my variable. So this is at 10 to the x. So in this case, what's playing the role of a is 10 in this scenario. So my derivative is going to be the natural log of 10, which is a number. Remember, that's nothing more than times 10 to the x. All right, so that's how we apply this. So let us do 3 simple applications. Suppose f of x equal 3 to the x plus x cubed. So watch here. Those are very different type of function. That's a power function, x cubed. That's an exponential, because in this scenario, the variable is a power. So what's going to be my variable? Sorry, my derivative. Okay, 3 to the x, that's a typical exponential with a equal to 3. So that's the base. So this is ln of 3 times 3 to the x plus x cubed is just a power. The derivative is 3x squared. Okay. I'll do one more and then we can proceed. Suppose f of x equal actually 4 times 5 to the x. Still simple stuff. Okay, so what is f prime here? Okay, I'll give you a minute to give me the answer on chat. You don't need more than a minute for that. Okay, you're missing one thing. Look, sorry, you're missing one thing. It's 4, that's a constant. We drop it, times the derivative of 5 to the x, which is ln of 5 times 5 to the x. Correct, all right? So let's see one more, f of x equal x to the power 3 times, let us say 8 to the x. So just mix match. All right, this one, absolutely, the product rule is in question. So this would give me the derivative equal, I'll write the derivative down here, equal, product rule. Here, because 4 is a constant, we just drop the constant, that's a product. Here is very different. The derivative of x cubed is 3x squared times 8 to the x plus x cubed. The derivative of 8 to the x is the ln of 8 times 8 to the x. All right, so that's our first formula for today. Sorry. Now we're gonna talk about the derivative of the natural log. So that's the derivative of the exponential. Part 2 is the derivative of the natural log. So they are basically formula that we have to learn and be able to apply them correctly. So, okay, derivative of the logarithmic function, which is very you guys are gonna use it a lot. So the derivative of f of x equal ln of x, the natural log. Okay, so how are we going to find the derivative of the natural log? So it's a little bit tricky, but the formula is simple. Graphically, let us see how the graph looks like. So we can practice sketching derivative. So this is x, and this is the natural log. And remember, the natural log is defined only when x is positive, and it goes like this. That's the natural log. So this is my y. Now, how does the derivative looks like? We're going to find it algebraically, but let us see how it looks like. So that's y prime. All right. So if I follow the slope, as we know, it's positive, 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 positive. And so the derivative is always positive, so it's going to be in this quadrant. And is it increasing or decreasing the derivative? What can you say? It is positive, but is it gaining value or losing value? The derivative of the log. You follow the tangent line. The tangent line is getting less and less and less and less steep. So the derivative is going to be positive, fine, but it's getting less. And the graph seems like it's almost flattening at the end. It means the derivative is less and heading. It's always positive, but it's getting smaller and smaller and smaller because the tangent line is actually becoming horizontal. Okay, so that's how the derivative looks like. And now let us find a formula for it. So what is the derivative of ln? Okay, finding it is a bit tricky. So we're going to proceed. So we have to find y equal ln of x. We need to find y prime. Okay. Now, if y is equal ln of x, so this tells me that, so now I'm in the process showing you how to find this derivative. If this is, it means e to the y is e to the ln of x. Now why I'm doing this? Because I need a formula for y prime. But we know what e to the ln of x is. E to the ln of x is x. Right? And now we're going to use implicit differentiation. So it's a little bit tricky. implicit differentiation. How we're going to use it? We said, okay, v to the y equal e to the x, and we know that y is a function of x, but I don't know the derivative. I'm actually kind of looking for it. So I say, okay, I take the derivative of both functions and set them equal to each other, equal to derivative of x. Now, what is the derivative of e to the y? Now, what does the chain rule tells me? Y is not a y. Y is a function of x. So that's my inside function. So what implicit differentiation tell me? So the derivative is, so the inside is y, the outside is the exponential. So it's the derivative of the outside evaluated at the inside, which is y, times the derivative of the inside. This is equal to 1. Remember, y prime is really what I am after. From here, I solve for y prime. That's what we did before. So I solve for y prime. I get 1 over e to the y. Okay. But now I go back to the original. What is e to the y? E to the y is x. It means y prime is 1 over x. Okay, and that will give me the derivative of my ln function. Now this is, in a way, agree with my graph. It means this is actually nothing more than the 1 over x. So my formula and my graph definitely agree. I cannot find a formula from the graph. I have to do it algebraically. All right, so the second very important formula of today is the derivative of the natural log. So we're going to proceed, write it, and then practice it a little bit. So if f of x equal ln of x, okay, very, okay. So the derivative with respect to x of ln of x is 1 over x. Okay. So now we're going to practice again this formula a little bit, and then we proceed. Okay. So example, find the derivative of the following functions. So I start with the, it's all simple stuff anyway. So let's start with some simple ideas. F of y equal ln of x plus 1 over x. Okay, so find the derivative of this function. Now, of course, we have a sum in here, so we have to know this. So what is y prime? All right. That's a sum. So I have to take care of each piece. This one, we just learned the formula for it. This one, I have to rewrite it so I can use the power rule. So I'll rewrite this as ln of x plus x to the minus 1. So my derivative is going to be the derivative of the ln, which is 1 over x, plus the derivative of x to the minus 1 is minus 1, x to the minus 1 minus 1. So this would give me y prime equal 1 over x minus 1 over x squared. Okay. All right, another example, but this time I want you to do it. Y equal ln of x squared plus 2. Okay, so what's the derivative of this function? You guys have to, like 2 minutes to do it and get me the answer. So how we are going to look at this function, that's crucial. Okay, anybody? What do you think we're going to use to compute, to find the derivative of this function? What do you think we're going to use? This is ln of x squared plus 2. We have an inside here, and we have the outside. That's a chain rule phenomenon. So what is the inside? Sorry, what's the outside? The outside is the ln function. So outside is f of u equal ln of u. Now what is the inside? The inside is the inside. That's my inside. It's x squared plus 2. So what's going to be the derivative? So the derivative is, the derivative of the outside is 1 over u, but evaluated at the inside. So it's going to be 1 over x squared plus 2. That's the derivative of the outside of the ln function evaluated at the inside, times it by the derivative of the inside, which is 2x. So the derivative here, another way to write it, is 2x over x squared plus 2. Okay, so now we have to use a chain rule. There is no way out. So that's my inside, and derivative of the outside, evaluated at the inside, times it, the derivative of the inside. Okay, let's take another simple problem like this. But this time I definitely want your answer. So suppose I take f of x equal ln of 1 plus 4 sine x. Okay, so I want f prime. Okay, this time you should be able to do it fairly, in a way, it is easier. Anybody? Either put it on chat or just say it in Word. What do you want me to write? What's your inside? What's your outside? Because I'm very quiet today. What's the outside? Outside is the ln of u. What's your inside? I'm copying
1 plus 4x, 4 sine x.
4 sine x. That's my inside. Okay, so now what's my derivative? The derivative of my outside, which is 1 over u, but we evaluate it at the inside. So that's the derivative of the outside, which is the ln function, which is 1 over the inside. You times it by the derivative of the inside. And then this would give me 1 over 1 plus 4 sine x. We times it by the derivative of 1 plus 4. Okay, derivative, that's a sum. Derivative of 1 is a 0. Plus derivative of 4 sine. 4 is a constant. The derivative of sine is cosine. Okay, and then it will be nice to write it like this. It's 4 cosine x over that. And that's f prime. Okay. All right, so of course, whenever we introduce a new formula, we have to introduce a composition, because that's how functions are built up. So once we have a composition, it means ln of something, and then the chain rule will have to show up, and we have to use it. Okay. All right. So For tomorrow, you have only those, not only those formula. Those are the new 2 formulas we're learning for tomorrow. I still have like 2 formulas and we will be done with formulation. But today, instead of giving you the last 2 formula, I'm gonna back up a little bit and talk about the derivative more as a rate of change. All right, so you guys have any questions about what we did? Very good. So now I'm going to go back and start again talking about the derivative and the meaning of it. So the derivative as a rate of change. So it's an idea that is spread around in your book. So you have a little bit of it in 3.1, a little bit of it in 3.3. So it's really spread out, but now we are ready to go back to it. Remember that for us, the derivative, we interpreted 2 things. We interpreted graphically as the slope to tangent line. That's really, and the second important one, it's a velocity. It means it's how fast the distance change with time. So those are the 2 interpretations that we worked with. How fast is the distance? That's what velocity is. Okay, how fast is the distance changing in time? The more your distance changes with time, the higher is your velocity. And in general, if your function is not necessarily distance, it's a population, growth, or anything, the derivative will tell you how fast is your function changing. And that's really what we will be talking a little bit about today. But first, I take you back to a very simple scenario. So before we talk about the derivative as a rate of change, let me ask you a fairly simple, I think, question. Okay, suppose I have the following, a population, that's a made up scenario. And the population changes with time. So that's a population, P of T, a population in certain country. And this is the time in years. And the population is in million. Okay. And we graph the population and we have this graph. So we realize that the graph is absolutely a straight line. Okay, so we graph this population, we get a straight line, which is usually not correct. Population doesn't grow along a straight line, but let us assume we have the scenario. And the slope of this line is a 2. Okay, now I want you to help me interpret the 2. What does the 2 represent in this scenario? So we have, this is a population, let me write word here. P of T represents a population in million, and this is in year. And I get the slope of 2 for this graph. So what does the 2 represent? What is your understanding of 2? Anybody? What does the 2 represent? I want a unit for it. I want an interpretation for it. So this is a line. What does the 2 mean? In this setting, the population double each year. And this is not correct. Because, let me tell you why, not because I said so. If the population doubles every year, what is the scenario according to you? If it doubles, I'm going to take a paper and follow your logic. Initially, it is 0. So this is T. So I'm trying to argue that. It's T and this is the population. If at 0, according to my graph, is 100. After 1 year, if it doubles, it's 200. If it doubles every year, it means it's going to be 400. Is this how the population behaving? That's what means the population, the slope is 2. Means I go 1 year, the population is going to grow by how much? How much this should be. If the slope is 2, giving a year, it's going to grow by 2. 2 million. Means after a year, it's not 200 million. It's 102 million after a year. That's the linear growth. That's not doubling. That's an exponential growth. Double is exponential growth. is actually we're adding 2 million every year. So one more year, the population is growing by 2. So the slope have a unit, and the slope is 2, and that's its unit, million per year. And that's very important. It means the population is increasing by 2 million each year. It's not by any stretch of the imagination doubling by 2. It's increasing by 2 million. It's a constant growth of 2 million per year. Now, suppose I take a point at certain year. I don't want to give you a year. And then I move a little bit. So this is from here to here, a certain change, delta t, okay? And my question is, if the time changed by that much, by how much the population will change? I'm gonna ask you, what is delta p in terms of delta t? My question is, find delta p, the change in population, in terms of the change in time. It means how fast is the population changing with time? So I took any point, this on the graph, any 2 points. As time goes from here to here, as time changes, the population is changing. My question to you is, can you express the change in population in terms of the change in time? It means how fast is the population changing with time in this scenario? So time change, population change. How fast is the population changing with time? Anybody can give me a relationship between the change in population and the change in time? Because usually that's what the derivative will actually tells me, this relationship between the change in the output and the change in the input. Anybody would like to give it a try? Okay, let me ask the following question. The change in population over the change in time in this particular scenario is equal to what? This scenario is equal to 2. I mean, I am not going to write 2 million because 2 is equal to 2, right? Which is 2 million. So if I take any point on the line, any 2 point, it doesn't matter, that's a straight line. It means, and I ask, okay, what's the ratio between the population and the time? The ratio is equal to 2. So it means that if I multiply by delta t both sides, it means the change in population is always equal to 2 times the change in time. I just multiplied by t. Okay, so this tells me that how fast is the population changing is that the change in population is actually twice the change in time. If the time changed by 1 year, population will change by 2 million. The time changed by 5 years, the population will change 2 times 5, which is 10 million, and so on and so forth. So the relationship between the change in time and the change population and time, the change of population is twice the change in time. So let us a little bit summarize. If my function is linear, it means the graph is a line. What's important about it? What does the slope of 2 tells me? The slope tells me that every unit of time, because it's linear, the population will change by the same amount. So the change is absolutely constant. And for this reason, the slope, unit of the slope is million per year. Million, change of population, unit of population per unit of time. So that's unit of population per unit of time. And then it tells me also that in this particular case, that the change in population over change in time is 2. So algebraically, I get the change in population is twice the change in time. So that's linearity. So if the slope increases, if the slope is 3, for example, it means that the change in population is always 3 times the change in time. So the population is changing really, really much faster than before. Now, as we know that most of the graphs are not linear. Okay, a lot of the graphs just curve. Okay, so this constant rate really does not occur in general. So let us take now another scenario. Let me take the following scenario. So example number 2. Again, I'm going to work with population because it's a fairly actually simple scenario to understand. So example number 2. Suppose I have a certain bacteria population. Okay, so we have a certain bacteria population. And it grows according to the following formulas. To the formula. Okay, P of T equal, so that's the population, 10 times 2 to the power T. So that's the population growth. And T is in hours. So we have a population of bacteria and it grows according to this formula. By coincidence, let me a little bit talk about how does this one grow. Okay, question number 1, does this population grow at a constant rate? So does it grow by the same amount every year? Yes or no, quickly. Okay, since I have 1 yes, I have an issue. Does this grow by a constant rate? And the answer is absolutely not. Let us watch how this graphically, this is going to look like this. That's a pure exponential. So let me take time and let me take t. At t equal to 0, this is 10. Sorry. 10, that's the initial population. After 1 unit of time, that's 10 times 2. So 10 times 2, that's 20. Okay, so it grew by 20. Okay, at t equal to 2. This is what? 10 times 2 squared. This is 40. So is it growing at a constant rate? Absolutely not. Only linear of all the graph, only functions whose graph is a line grow by a constant rate. Whenever the function curve, then the rate is not constant. So at 2 is 4, so definitely it's growing. From here to here, it grew by 10. From here to here, it's actually growing by 20. And then you keep going. So the rate is definitely not constant. It's not growing at a constant rate. And if you graph it, so before I ask any questions, even on the graph, we can see that. If we graph, we're going to get something like that. And even if we graph, if 1 unit, it grew by that much. Another unit is growing way, way, way more. 1 more unit, absolutely more. So you can see absolutely not a constant rate. Every unit of time, and this is growing faster and faster and faster. So it's as far away from being a constant rate as possible. Okay, and comment because one of you mentioned that this is a scenario where the population is doubling every unit of time. That's actually, as you realize, that's a population that is doubling, not increasing by a constant rate. It's actually doubling every unit of time, 20, 40. If you find it at 3, you're going to get 80. So that's a population that doubles. That's a typical exponential growth. And that's how bacteria grow. Bacteria don't grow linearly. All right, so that's so my graph is, I will draw my graph in here. This is a 10. And that's my growth. And this is time in hours. And this is my population. Okay. So definitely not a constant growth at all. Now, my first question is going to be the following. I'm going to ask you to find the average rate of change. It means on average. So find the average rate of change. You have to remember that average rate of change. And on average range of change of the population for the following time, for t between 1 and 10. and 10. So what does, let us remember the definition of the average rate. It means at t equal to 1, that's 1, and t equal to 10. Okay, during this time, the population changed because as time went from here to here, the population, we were right there, and the population increased. That's the population at 10. And that's the population at 1. So as time went by, between t equal, since we started the experiment of counting those bacteria, between t equal 1, t equal to 10, the population actually changed a lot. And now my question is, what's the average rate? So let us see how we compute the average rate. The average rate is how much the population changed between those 2 time interval. So that's how much is changed. So that's the change, how much is changed, divided by how long it took to change that, divided by 10 minus 1. So the numerator tells me how much is changed, like the distance, how much population change. Always remember the scenario of the distance. When we compute the average velocity, how much we moved over how long it took. That's really the same principle. And this is how much over how long. Okay. Now, how much the population changed is, okay, we just plug in back into the formula, and the formula was 10 times 2 to the t. So it's 10 times 2 to the power 10 minus 10 times 2 to the power 1. So that's the change in population over 9. So let us see unit here. The unit here is bacteria, number of bacteria. That's how many bacteria changed, and it took 9 hours to do this change. Now we can actually pick up our calculator and compute those numbers because they have a meaning. So I do that. So I will compute. Okay. And this is telling me my calculator is low on battery. So I have to change that when the lecture is done. To the power 10. I'm doing this. Minus. Right. So I got the following. The numerator is 10,220 over 9. Again, the unit. This tells me by how much the number of bacteria changed. It means between the 1 hour after we start to expand, 10 hours, the number of bacteria changed by that much. That's the change. So this is the numerator is number of bacteria. And this is going to give me how long it took. So now when I find the ratio between them, I'm getting 1,135.5. And what's going to be the unit here? What is the unit? I want unit. What does this mean? What does this number mean? I took the ratio, I got the number. What does this number mean? Back to you. It's crucial. So when I take the change of population over change in time, I got the number. What does this number mean to you? Quick, I want answers. Bacteria per hour, it means on average. It's bacteria per hour. Bacteria per hour, it means on average, and that's crucial. On average, the word average here is crucial. It means between t equal to 1, t equal to 10, those bacteria were growing on an average of 1,135 per hour. And that's the average. Now the question is, was it growing by that much every hour? Definitely not. Okay, but that's it, average that much. But if I take after 1 hour, was it growing? Did it grow by 1,135? No, because as we realized at the beginning, it wasn't growing fast. It's at the end where actually the growth is much faster. But this tells me on average, it grew that much. Okay, but this doesn't give me information about here, after 1 hour, what's the growth rate? How fast was it growing after 1 hour, because on average it's that much. But now I'm gonna zoom in. I said, okay, but I feel that after 1 hour, the growth wasn't fast. After 10, the growth was very fast, because here, I mean, the function is really growing fast. So now my question is, how fast was it growing at t equal to 1? And now I'm gonna zoom in. I'm gonna compute the derivative and try to make sense a little bit out of it for us. So what does the derivative represent? So this is my problem. I'm not changing my scenario. I'm gonna take the following. So first I'm gonna ask a question, a very simple question, and then we're gonna analyze it. So now this is question. Now my population is always the same formula. I'm not changing. I'm rewriting it. To the power t, that's nonsense. Okay, and now the question is the following. Find the derivative at p. So dp, because that's the change of population over change in time, and I want it at t equal to 1. I use this notation on purpose because it means basically I want the derivative at 1. Simple. And then we're going to try to understand what does this a little bit represent. All right, so what's the derivative at 1? So first we compute the derivative using the new formula we just learned. Tan is a constant times 2 to the t, the derivative is log of 2 times 2 to the t. That's the derivative. So at 1, it means I plug in 1 for t, I'm going to get 10 times ln of 2 times 2 to the power 1. And then I use our calculator to compute. And this will give me, my calculator gave me 10 times, how much? ln, what is the ln? ln of 2 times 2. So my calculator gave me 13.86. Okay, now we're going to try to interpret this number. What does this number actually mean to us? What's the unit of this number, and what's really going on? All right, first, let us remember, what is really this derivative? How did we compute the derivative? What did we actually do when we computed the derivative? What we did was the following. Let us remember what we do. Always remember the velocity. We took the change of the population, that's really what we did, over a small interval of time. That's what we did. And then we divided by the change in time. That's what we did. So the derivative was, this is almost, that means when h is small, when h is very, very small, this ratio is almost equal to 13.86. Okay, so how we found the derivative, that's what we did. We actually did the following. This is at 1. The derivative is how fast, also population changing over a small interval of time. And we took 1 plus h. That's really what we did. And what we computed is the average rate over the small interval of time. Because our logic was, if you find the average rate over a small interval of time, we know much better how fast it is changing. Right, so I want to analyze this statement. First, what's the unit of the average rate? What's the unit here? When I compute the change of population over the change in time, this is time, and this is population of bacteria. So the unit here is bacteria per hour. So the unit we're going to give to the derivative is going to be bacteria per hour, because it's going to inherit the unit of the average rate. So the unit of the derivative is bacteria per hour. But now let us a little bit understand what does this number tells me. So this number tells me the following, that it's like a slope. It means that the change of population here over the change in time, so the change of population over the change in time, this is almost equal to 13.86, almost equal. So let's write this down. It means that when h is small, and that's the hardest part, when h is small, I'm going to multiply this by h. multiplied by h. When h is small, it means the change of population over a small interval of time is almost equal to 13.86, which is the derivative, times h. And that's the idea I want to emphasize the most. So when we compute the derivative, basically we computed the average rate over a small interval of time, that's 13.86. It means that the change of population, when h is small, how fast is the population changing with time? The change of population is almost equal to the derivative. So that's the derivative times the change in time. So this tells me how fast is the population changing with time. So in other words, we can write this is that the change in population is almost equal to 13.86, which is the derivative, times the change in time. So the change of population is that number, think of it as a multiplier, times the change in time. So the higher is this number, the higher is the derivative, the faster is the population changing with time. The higher the derivative, the faster the population is changing with time. So if I take, suppose I tell you find p prime of 10. Okay, I compare that. P prime of 10, if I find it, I will get 10 times the ln of 2 times 2 to the power 10. And if I plug in all those numbers, I will get 7,097 bacteria per hour. What does this mean to you? It means at time t equal to 10, when you are near 10, if you change the time a little bit, at 10, the population change by that much times the change in time. So the change in population near 10 is 7,079 times the change in time. So you can see how much faster is the population changing with respect to time. This is near 1, and this is near 10. So in near 1, if you change the population, let us change time by half an hour, the population will change by 13/2, almost 6 bacteria. After 10, if you change the population by half an hour, this is going to change by 7,000/2, which is going to give me 3,500 bacteria. So the change here is very slow respect to the change here. So in this sense, what the derivative is really telling me is how fast population change with time. And that's really what the derivative really tells us, how fast my output is changing with respect to my input. Okay. All right, at this note, I have to finish. So please, your math lab homework is on is already there, do it. And think about those ideas a little bit for tomorrow. I will do one more problem along those lines because that's the only way we can understand this idea of derivative. All right, any questions before I let go? Okay, thanks guys, see you tomorrow.